Thus far, we've seen various examples of sets, collections, which arise in various kinds of applications. It'll be useful to have in mind a generic abstract set on which we are going to be pinning our analysis. And so let's begin by thinking about some abstraction for all of this. At the back of our minds, in whatever application is at hand, we will be dealing with some set of possibilities, a universal set. In the theory of chance, we will frequently call this the sample space. We are imagining that we are actually sampling, picking out elements from this collection, from this basket of possibilities. In the theory of probability, the standard representation for a universal set, the sample space, is the uppercase Greek letter omega. And we will from now on represent an abstract setting, a universal set, by uppercase omega. What about the elements of the set? Well, the elements of the set are denoted then naturally enough by lowercase omega, and we will say that these are the elements of the universal set, or the sample points of the set. In specific settings, we will dispense with this abstract notation and use notation that tradition compels us to use. So, for example, if you're dealing with the natural numbers or the integers, we'll use blackboard bold Z. And we'll represent typical integers by letters like N, or occasionally I, J, K, L, or M. If you're dealing with a real line, we will use blackboard bold R instead of capital Omega, and represent generic members by X, Y, Z, occasionally U or V or S or T. And if you're dealing with functions, say continuous functions, we will represent them by script C, and of course a generic function is represented by F, occasionally G or H or something else. We will not be hidebound and insist on staying with notation, which is traditional, if circumstances tell us it will be better to use some other description. But of course you understand these are natural, normative descriptions of these kinds of objects. Now, it'll be convenient to have a short mathematical notation to say this is an element of this set. Right? So let's say we're dealing with a universal set, an abstract set, uppercase omega. We will indicate membership of uppercase omega by saying an element, little omega, is an element of uppercase omega, and we have a short mathematical notation meaning all of that. And we will consistently use this standard notation. So here is one abstract setting at one end of the spectrum, an abstract universal set, uppercase omega. At the other end of the spectrum, we have the trivial set, a set with nothing in it. Now you wonder, why would we bother with something which has nothing in it? Well, it's because, as a preview, we are going to be able to do algebra on these objects. The kind of arithmetic in algebra that you're very familiar with from elementary school and middle school. And of course, when you do arithmetic or algebra, we have an idea of a zero. The empty set, and here is a standard notation for it, a circle with a cross line through it. This represents, in a fundamental sense, a zero in the idea of an algebra of set. For us, the empty set is a set which has no elements in it. Okay, so thus far we've now built up some language, some way of describing collections of abstract objects. Where do we go from here? The next setting is to consider sub-collections of these objects. So bear in mind that at the back of the experiment there is always a universal set of possibilities, omega. And we are going to be dealing with elements from omega. Now, a sub-collection of these elements from omega is called, naturally, a subset. And the mathematical notation compactly on the right of the screen tells you how we can describe these subsets. So that notation says A is a sub-collection, it is a subset of this bigger set, omega, in this case the universal set. Now, Abstraction is all well and good, but we respond well to visual stimuli, and some visual representations sometimes are very useful for seeing the relationships between various abstract objects. In the setting of sets, these visual representations are called Venn diagrams, and I've given you here on the screen a representation of a subset of a universal set. I've represented the universal set by a rectangle, that's omega. You should think of the elements of omega as points in that set somewhere, and a subset shown naturally as a blob inside this collection. It connotes a sub-collection of the elements of omega. You should bear in mind that this is purely for visual representation. There is no intent to convey any kind of geometry. Area doesn't mean anything here. This is purely a representation on paper of an abstract object. And sometimes these representations give us some kind of cue as to how things interact with each other. Well, this is all very abstract, right? So some concrete examples might allow us to settle these concepts. Well, what are the simplest examples of subsets? Well, the simplest examples are, well, A could be omega itself. Omega itself is a subcollection of itself. In other words, if your subcollection contains all the elements in the original set, it is the original set, and here's a trite and simple subset. At the other end of the spectrum, if your set A has got no elements in it, in other words, it is the empty set, that is also patently a subcollection, a subset of the whole. Of course, these are trite and obvious. Let's stitch together some more interesting examples to settle the concepts. So let's begin with the setting where, let's say, we throw a die. We identify pips by numbers, 1 pip through 6 pips with the numbers 1 through 6. This is the dictionary of translation that we agree on ahead of time. The set at hand, the universal set, is then the collection of numbers from 1 through 6 in any order you like. Suppose I am interested in a throw which exceeds 4. This describes a subcollection, a subset, and we identify it as the elements 5 and 6 together. And so now we have a subset A consisting of elements 5 and 6, which is a subset of the set of possibilities, the numbers 1 through 6. Let's pick an example from the second example I've shown you on sets, from graphs. Imagine a graph on a certain number of vertices, say n. The family of all such graphs is potentially a large family, if n is large. For example, you could imagine a setting where we're looking at flights between cities, cities representing vertices in a graph, edges between cities showing that there are direct flights between cities. And now we can understand, well, here's a setting for transportation. This gives us a family, a set, a universal set, the set of graphs. Those graphs, which, for example, let's say have 2 edges, represent a subcollection, a subset of graphs on these. Still another example, and let's now go on into the domain of numbers. The collections of prime numbers have drawn interest since antiquity, and in the modern day are vitally important in electronic commerce through providing security through cryptography. Prime numbers are at the heart of cryptographic protection schemes. The collection of prime numbers, the numbers 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on, Euclid knew there were an infinity of prime numbers. Okay, and you might have seen a proof of this in an elementary class. But the collection of prime numbers clearly is a sub-collection of the collection of integers. The prime numbers are a subset of the integers. If we move on to the real number line, we can think of other rich collections, sub-collections of the whole. For example, fractions, in other words, rational numbers, denoted by blackboard bold Q, is a subset of the real line. Right. So we now have an understanding of what subsets might mean, and we think of Venn diagrams as ways of representing visually relationships.